What's up guys, welcome to another video. In this one I will be solving this very interesting looking integral. It's the one from 0 to infinity of inverse tangent of x quantity squared over x squared. Surprisingly, the result is pretty nice, so let's get into it. The first thing I want to do is a bit of integration by parts. So I'll be using the DI setup, but if you use the UV method it gets you the same result. So I'll be differentiating inverse tangent of x squared, and I'll be integrating 1 by x squared. On the left we get 2 inverse tangent x, and with the chain rule 1 by 1 plus x squared, and on the right we get minus 1 over x. I'll get this multiplied, which gives us a minus inverse tangent squared over x evaluated from 0 to infinity. And I'll just give myself a bit more space. To that we should be adding these two to get multiplied together, so we get twice the integral from 0 to infinity of inverse tangent x over x 1 plus x squared dx. Now on the left, this evaluation is pretty easy. In both cases it goes to 0. It's easy to see for infinity because we're just dividing something finite by infinity, but for 0 you can use something like L'Hopital's rule or something and verify, but it indeed goes to 0. So we have twice the integral from 0 to infinity inverse tangent x over x 1 plus x squared dx. Now I think the substitution is pretty obvious. We're letting inverse tangent of x be equal to u, because the derivative of inverse tangent is 1 by 1 plus x squared, and well, we have that in our function. So we're left with twice the integral from as x goes to 0, u also goes to 0, and as x goes to infinity, u goes to pi by 2. So inverse tangent x is u times 1 by x. If you take the tangent on both sides here, you get that x is equal to tangent of u. So 1 by x is just the cotangent of u. And dx divided by 1 plus x squared is just du. So we have this pretty interesting looking integral. And we're going to be doing integration by part again. So again, di, I'm going to differentiate u and integrate the cotangent function. If you don't know how to take the antiderivative of cotangent, it's pretty easy. You just let it, you just write it in terms of cosine and sine, and you let t be equal to sine u, for example. So you get 1 by t integrated with respect to t, and that's just log t. So we have log sine u. Right. So we're going to evaluate this multiplied together, so we have 2 times u log sine u evaluated from 0 to pi by 2 minus integral from 0 to pi by 2 of these two multiplied together is just log sine u du. Again, the evaluation is pretty easy. Both cases it goes to 0. When you evaluate it at pi by 2, you get log sine pi by 2. Sine pi by 2 is just 1, log 1 is 0. And at 0, you have kind of an x log x case. You can just use L'Hopital's rule for that again. So we're left with negative 2 times the integral from 0 to pi by 2 of log sine u du. And this is a pretty well-known integral. You might have seen it already in other videos. People reference it as Euler's log sine integral, and I could just tell you the result because it's well known, but we're going to derive it here. So I'm just going to call this, I don't know, like j, and move forward with evaluating it. So we know j is the integral from 0 to pi by 2 of log sine u, and I want to invoke the substitution u equals pi by 2 minus x. Now this implies du is equal to negative dx. So we're going to get the negative we have the integral from as u goes to 0, x goes to pi by 2, and as u goes to pi by 2, x goes to 0. So we have flipped bounds, which we can take care of using the negative sign out front. So we now have an integral from 0 to pi by 2 again of log of sine u becomes pi by 2 minus x, Mr. Parenthesis, dx, sorry. Now some of you might know, but sine pi by 2 minus x is just cosine x. It's a nice symmetry that it has, so we can replace this with cosine of x dx. So we know j, it doesn't matter if you put a sine or a cosine in there, it's still the same result in the end. So both of these are j, and what I want to do is I want to add those up. So on the left hand side we're going to get 2j, and on the right hand side we're going to get a sum of two integrals going over the same bounds. So that means we can combine those into a single integral going from 0 to pi by 2. And since we're going to get a sum of logs, we can use log identities to combine those into a singular logarithm where the inside is the product of the two functions. Now notice I had sine u up there and cosine x in there. The dummy variable doesn't matter because in the end it's just a number. So here you could just perform the substitution of letting x be equal to u and proceeding, but there's really no point in that. So how do we proceed from here? Well, we notice that cosine x times sine x is 1/2 the sine of 2x. And because we have a product of two things in that log, we can just split it up. So we have 2j is equal to 1 integral from 0 to pi by 2 of log 1/2 dx plus integral from 0 to pi by 2 log sine of 2x dx. Now for the first integral, it's pretty easy to see what it evaluates to. It's just pi by 2 times log 1/2, which is the same as negative pi by 2 log 2. Then here, I want to perform another substitution. It should be pretty clear. I'm going to let 2x be equal to u, which implies dx is 1/2 du. So we have 1/2 out front, integral from 0 to pi of log sine u du. Now I'm going to do two things. I'm going to multiply by 2 on both sides just to get rid of these denominators. So we're going to get 4j negative pi log 2 plus. And I'm going to split this integral into one going from 0 to pi by 2 and one going from pi by 2 to pi. Now you'll notice the integral from 0 to pi by 2 of log sine u is just j. We had that up there. So I'm going to write this as j plus the integral from pi by 2 to pi of log sine u du. Again, one last substitution. I'm going to let u be equal to x plus pi by 2, which implies x is equal to u minus pi by 2. So I'm going to subtract this j. That means we're going to get 3j is equal to negative pi log 2 plus the integral from as u goes to pi by 2, x goes to 0, and as u goes to pi, x goes to pi by 2. Then we're going to get log sine, and u becomes x plus pi by 2 dx. Now another nice symmetry of the sine function is that sine x plus pi by 2 is also the cosine of x. So we have a log cosine x here. And would you look at that? Integral 0 to pi by 2 log cosine x, it's also j. So we can subtract it on both sides and get that 2j is equal to negative pi log 2. Now if you remember up here, I was negative 2 times j, and here we have 2 times j. So if I is equal to negative 2j, then that means we just slap a negative out front here, and we get that I, which was the integral from 0 to infinity of inverse tangent of x squared over x squared dx is equal to pi natural log 2. Quite simply and quite beautifully indeed. Now this is the end of the video. I hope you liked it. If you did, make sure to like and subscribe, as it would really help me. Make sure to also write down suggestions for future videos in the comments. I would really appreciate those. Alright, see you in the next one.